Okay, the next topic in our is dealing with insoluble salts. Now we're going to look at both soluble and insoluble to get the difference between the two, taking this problem right here. In the script, I gave you a number of ions that are included in an ionic compound that will make it soluble. And when it's soluble, it's single arrow. If it's insoluble, it's double arrow because a little bit is soluble, but not very much. So in the case of part A, we're asked to write an equation showing this. Sodium is a group 1 metal. It is going to be soluble. Nitrate is one of the nitrogen oxygen family ions. Also makes it soluble. So either way, you start off with a solid before the water is introduced, single arrow because it has two elements. It only needs one or two ions that will be soluble in water. But we must put H2O above it to show that water is the medium at which this reaction is run. Sodium is a group 1 metal, like I said, so it has a positive 1 charge as an ion in water. So we put aqueous for that. And the nitrate, according to your polyatomic ion chart, has a negative 1 charge, and that will be aqueous as well. And there is your dissociation or dissolving reaction for that compound. Strontium iodide. Strontium iodide, strontium is not a group 1 metal, iodine is not on the list. There's iodine oxygen family, but this is not iodine oxygen, this is just plain iodine. And you have a chart in chapter 18 that you need to use, which is on pages 772, 773. If you look for strontium iodide, it's not on there. It might be in the back, I'm not sure. But regardless, it doesn't have the qualifications for this being single arrow. So I'm going to say that this is an insoluble salt and use a double arrow to show that it is just the tiniest bit soluble. Again, should put the solid here and H2O above the arrows. Strontium is a group 2 metal, has a positive 2 charge, so SR2 positive, and what little bit actually dissolves will be aqueous. And iodine is a halogen, group 7A, negative 1 charge, and there's 2 of them, so we put the 2 in front because iodine, while it is diatomic as an atom, it is not as an ion. So this will be I negative, and that will be aqueous. And that's all you have to do for that. Okay, so if it's on your charts that I designated in your notes, it's insoluble. If it's not one of the ones that has the automatically soluble or single arrow reaction, then we use the double arrow. That's the bottom line for part C. For number 21, we're asked to give, well, that's weird. That. See there? Good job, me. Okay. We're asked to write the Ksp expressions for this. Okay, so we do the dissolving thing. These are both insoluble salts. So these are both double arrow reactions. So strontium sulfate, calcium phosphate, both insoluble in water. Put the solid there. A little bit will dissolve. And how will it dissolve? Well, we're going to get a strontium. Now, strontium is a metal group 2A, so that's a positive 2 charge. That would be aqueous. Plus, sulfate is a polyatomic ion with a negative 2 charge, so SO4 2 negative aqueous. So that means then that the Ksp expression, which is what we're looking for here, is going to be SR2 positive, concentration, times the concentration SO4 2 negative. We don't put this in here because of the salt. Okay? Do the same thing over here. Calcium is a positive 2 ion because it's a metal group 2A. We have 3 of them. There's no such thing as Ca3 as an ion, so we put the 3 in front to show that we have 3 calcium ions. That'll be aqueous because that's the small amount that will actually dissolve in there. Phosphate is a polyatomic ion, and we have 2 of them. Put 2 in front, but we don't put the parenthesis in the products because it's not combined with anything, it's by itself. So we just put PO4. You find the charge of that in the polyatomic ion chart as a charge of -3 or 3 negative, and that'll be aqueous. Now, to write the Ksp expression for this, it's going to be the concentration of calcium, and this coefficient becomes an exponent right there. So calcium 2 positive cubed times the concentration of PO4 3 negative, and this coefficient becomes an exponent squared right there. And there's your Ksp expression for calcium phosphate, which, by the way, is the formula of the substance that makes up teeth and bones. Number 23. We were given here a solubility of 0.0072 grams per liter. And it wants to know what the Ksp is for this. Well, let's do the dissolving reaction for AgBrO3. AgBrO3 does not have anything. Well, it actually turns out that BrO3 is one of those compounds or ions that will that will be soluble, but the silver is an extremely insoluble metal. So I'm suspecting, since the solubility is given to us as this, that this is a slightly soluble, which technically means insoluble salt. But when we write concentrations, it's in moles per liter. So what we have to do is we have to change that to grams per liter. So we put grams on the bottom, moles on top, 1 there. And then we go to our periodic chart. And silver is 108. Bromine is 79.9. And we have 3 oxygens, so 3 times 16.0. So when we add all that together, 188 plus 48 is 236. So we'll put 236 right there for 1 mole of that. So I take my calculator out. So 0.0072 divided by 236 gives me 3.05 times 10 to the -5 moles per liter. And that's going to be my X. That is how many moles per liter are going to dissolve in water. And so when I write the reaction AgBrO3 solid, double arrow, because it's going to be a really small number here. So it's going to be Ag positive, aqueous, plus BrO3 negative aqueous. Now how did I know silver was positive 1? Because bromate, it turns out, is -1. One other thing too, and it might help you save some time in doing homework, silver is one of those transition metals that has only 1 charge. So we put a plus. In fact, when you name silver, you don't have to say silver 1 bromate. You just say silver bromate because there is no other charge for silver. So now we can write the Ksp expression for this. The concentration of silver by whole times the concentration of bromate. Now, to get an idea, kind of like what we did with the acids and bases, even though we can't put this in the denominator because of the fact that it's solid, we do have a chunk of this stuff, and that's the international symbol for chunk. And that a little piece of that chunk is going to be lost, so we'll go minus x there. And this gives us x over here and x over here. So that is going to allow us to come up with an x for this and x for this. So this gives us x squared. Now we said x already is 3.05 times 10 to the negative fifth, and that's going to be squared. So our Ksp, 3.05 e negative 5 squared is 9.30 times 10 to the negative 10. And there's our Ksp. Right? Number 25. Same thing here, it's the same kind of problem. The only difference is now we've got multiple ions of one type. And that has to be taken into consideration. And this is going to be a little bit of a problem, so I want you to focus hard rather than have your eyes glaze over like some of you do when you watch my videos, if you watch my videos. So we're going to have to find the molecular mass for this. So copper is 63.5 plus iodine is 127, I believe. Yes, 127 plus oxygen 16.0 times 3, close parenthesis, times 2. Wow, what a mess. So let's punch this out, 63.5 plus parenthesis. And it really helps to write the parenthesis and the time sign exactly the order of the compound. That way you don't forget something. 127 plus 16.0 times 3, close parenthesis, and then times 2. And I get 414 rounded off to 3 sig figs.